Okay, let's get this quadratic functions party started. We're going to spend a lot of time just focusing on the ins and outs of the vertex of this function f of x equals 2x squared plus x minus 1. The vertex, of course, being the turning point. So either we're concave up or we're concave down, and there's some kind of a turning point, which we can achieve by way of completing the square using this x equals negative b over 2a structure that is in your formula booklet. And we'll connect it to this abstraction here and give you a little bit of a sense of where this stuff comes from. And of course also the GDC. So let's actually take a paper 2 approach and work backwards from a GDC result. And then we'll be able to confirm the other two, parts A and B, after we do C. So you should be pretty comfortable with simply putting y sub 1 is equal to 2x squared plus x minus 1 into your GDCs, into your y equals spread, that menu there. Excuse me. And after you graph it, I tend to go, as I've mentioned, zoom 6. It gives me a standard factory preset window of negative 10 to 10, negative 10 to 10. I then actually went and zoomed in a little bit further into the origin, so you see a blow up here that actually is a much clearer, more enlarged picture to work with. And of course, when you go to your best friend right now, second calc, which will bring up this menu here, you're going to grab the minimum feature, and that's your classic left bound, right bound. So wherever that cursor showed up, of course, you've got to arrow over and get to the left of what you are interested in. So our vertex, of course, is right there. That's our turning point. So over here, we just click randomly. It sets a left boundary, then you got to get over to the right and click on that. It does this weird guess thing, and then when you enter again, there it is. Boom, it shows up. Light indication here. There's the actual turning point. And the minimum is indicated, interestingly enough, down here, the x value and the y value. We'll come back to this, of course, later. This is the GDC doing the best it can to give you an x value that appears to be negative 0.250014-ish. Sometimes some GDCs might show you negative 0.24999-ish. So this is what I call cheap technology. It's doing the best it can with chip technology to give you a value that may or may not be accurate. But of course, if you're writing this down to 3 sig figs, you're writing down negative 0.250 and honoring the third level of significance. What do we have over here? You might be interested to know, if you don't know, that if you go alpha in green and then find the x and y cells and bring those guys back, those x and y values that you found here, they were stored automatically by the GDC in your x storage cell and your y storage cell. Again, this one looks exact, this one looks a little bit messy, and we'll come back to that. So we have a goal. We know that we have a concave up parabola turning at what appears to be negative 0.25-ish, comma negative 1.125. So let's move on. Let's work backwards, continue to work backwards from C, which we just did, to B, using this guy here. So that's pretty straightforward. Of course, A is 2, B is hiding as 1. Sometimes people grab X because they don't see the 1 there, and that kind of messes everything up. Be mindful of that A, B, and C, of course, are numerical values, and C is critically negative 1. So where x is supposed to be negative b over 2a, you're just simply plugging in a of 2, and not surprisingly, well, maybe semi-surprisingly, negative 1/4 shows up. That's exactly negative 0.25. So we've already kind of fleshed out a limitation here in terms of what the GDC is giving you based upon technology as a kind of a way of knowing. So the y value is simply the function evaluated there, right? That's all that that's trying to say. And so f of that value, negative 1/4, if you crank it out and do the arithmetic, lo and behold, negative 9/8 comes into your life, and negative 9/8, as it turns out, is negative 1.125. So that one came out okay in terms of the technology, giving you the correct, fully correct, accurate result there. We'll come back to where this, or how this may have come into your life. For right now, it's just kind of magic, all right? Which I'm not a big fan of magic in the mathematical realm. It should be a bit more rigorous than that. So now let's move on to completing the square. That is pretty challenging. I must say that for the SL level, if you're an SL student viewing this, that maybe this is a little bit too intense when it comes to an IB expectation, but it certainly would be a higher level expectation. But the interesting and important points to be made as we go along are still worthy. So let's go through it, even though it looks rather menacing. So one way, there's two different ways basically to approach completing the square. One way would be to say, well, let's just talk about y being equal to that, and let's throw that constant term right away over to the other side, because the actual process of completing a square applies to just the variable components. Then if you divide both sides by 2, you end up getting something like that. You can call this x over 2, but it's not as easy to see what to do next. So let's think about x divided by 2, because of course that divided by 2 just frees up the x squared. So x over 2 is really best thought of in this context as 1/2 of x. So now we're adding something to both sides. And the thing that we're adding to both sides here, at this stage, regardless of what this right-hand side looks like, you take half of whatever this b value is, right? This value that's in front of the x, that's kind of like your b value, if we're talking ax squared plus bx plus c. So half of that's squared. Well, 1/2 times 1/2 is 1/4, and 1/4 squared is what you end up adding to both sides. And that is supposed to be the process that actually completes the square on this right-hand side. So all I did was multiply this out, of course, and the future of that, if you actually think about how to factor that, is down here as this perfect square. That's the whole point. So what I did here on the left-hand side, I just certainly squared that out. So there's my sort of 1 over 16. And then I just multiplied top and bottom here by 8. So I had to get a least common denominator. And that's where the 8y and the 8 times the 1 comes from. So I wanted, because I had the 4 squared for 16 here, I wanted to multiply top and bottom by 8 to get the same denominator so I can put everything over the 16. Then, of course, 8 plus 1 is 9, and this guy factors. You might have a think about that, because the first outside, inside, last would give you 1/4 x plus 1/4 x, better known as 2/4 x, and 2/4 x, of course, reduces to a half x as a middle term. So I know there's a lot going on here, and now we just have to sort of unravel this to get y by itself again. Best way to do that is multiply both sides by 16, and all I did was save some time. I multiplied both sides by 16, so it kills off the 16 here on the left, and I threw the 9 over to the other side right away to save a little bit of time. Divide by 8, and we get this new form. So again, it's a little bit more higher level than standard level, but if you recall anything from graph transformations, we've taken an x squared parabola graph, we've actually shifted it 1/4 units to the left and 9/8 units down, and of course we've doubled it, so it's gone up faster. So the vertex ends up just being the opposite of that. There's the same number, the negative 1/4 that we saw in the previous two methods, both technology and negative b over 2a based. And then of course when x is negative 1/4, that zeroes out, and your lowest possible value is going to be negative 9/8. Some cultures prefer this method. You might like it a little bit better. All you've got to do is factor out the 2. So if we just focus again on the x variable component, if I take 2 away from there, I get just x squared, because 2 times the x squared would be 2x squared. And if I factor 2 away from 1, of course I get a half, right? Because that times that would give me back the 1x. And of course the negative 1 just came down. So in a similar sense, here's the sort of b piece. You need to take 1/2 of that and square it. And of course the 1/2 times that is still a 4th, and a 4 squared is still a 16th. So we're adding a 16th in there, because that's going to be completing the square. But you're not really adding a 16th in there, because twice 16th is really 2 over 16th, or an 1/8. So that's really adding in an 1/8. And of course you just can't add an 1/8 in, so we subtract an 1/8. So basically 1/8 minus an 1/8, net effect is 0. So we didn't change anything going from this step here to this step here. So this guy factors. That's going to be the future. Once again, there's your first, outside, inside, last becoming that multiple. So there she is right there. And of course negative 1 minus an 1/8 is negative 9/8. And we're good to go. Same exact answer. All right. So maybe that's a bit more palatable for you when it comes to some cultures that prefer to do the method of complete the square that way. Okay, a couple of sort of theoretically based thought-provoking questions for you would be this x equals negative b over 2a thing I've highlighted here in green. Think about down here with the actual quadratic formula, and x is equal to, look at that, negative b over 2a. And there's something about the discriminant here. Do you think it's coincidental that this negative b over 2a is showing up down here as part of the quadratic formula? And then, what if, for example, the discriminant was 0 and you just ended up having negative b over 2a? How might some of that thinking play a role to support why this actually works? The final thing I might say to you is if you've done already some calculus in the course, some of you have, and if you're ever viewing this when you haven't, there is something called differential calculus, or the derivative. How might the derivative play a role when it comes to actually trying to find some kind of a turning point? Well, of course, that would be where the slope of the line drawn tangent is 0. So you might want to actually differentiate this guy and check that out, right? 4x plus 1 is our derivative. And what's that got to do with this magical 1/4 or negative 1/4 that interests us? Okay, pretty daunting, that method there. That one's more palatable. Gave you a few things to think about there. That's pretty much it for this podcast. Thank you.